boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to this week's Naked Scientists with Helen Scales. Hello, Helen.
Hello.
And with me, Chris Smith. Now, coming up, a device that's inspired by a mosquito, and it could help diabetics to painlessly monitor their blood sugar levels, and that's because scientists have stolen the trick that they use to creep up and bite you on unawares. Also, why every cloud doesn't just have a silver lining. It also has a lead one, it turns out, and we'll be finding out why leaded petrol could have made the world cloudier. Plus, we'll be looking at the emerging swine flu situation in Mexico and asking where did it come from and what risks does it pose? Helen.
Thanks, Chris. Also, this week we're looking at the science of atmospheric chemistry. We'll be hearing how scientists are working with local councils to check their air quality and pollution levels in cities, and how researchers have developed a new mobile monitor that pedestrians can carry around town, and it produces a real-time readout of what air they're breathing in and what's in that air. We'll be putting that to the test a bit later in the show, and we'll also be hearing how seaweed could make a surprising contribution to the world's weather.
Indeed, thank you, Helen. You've heard the old wives' tale that a piece of seaweed can tell you whether it might rain later in the week. Well, in fact, seaweed could actually be responsible for making it rain in the first place, and we'll be hearing why. In the meantime, if you'd like to get in touch with the programme, you can send in your questions. The email address here is chris@thenakedscientist.com.
The Naked Scientist Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
You're listening to The Naked Scientist. Now first this week, a new high-tech gadget has been invented that was inspired by the humble mosquito, and it could one day provide diabetic patients with a portable artificial pancreas that would help painlessly monitor and control their blood sugar levels. Well, the electric mosquito, or e-mosquito, was invented and patented by Martin Minchev and Karen Kaler, who are electrical engineers from the University of Calgary in Canada. And they modelled this on the piercing, sucking mouthparts of mosquitoes. This e-mosquito device is currently about the size of a deck of cards, and it contains 4 microneedles, and they're about twice the diameter of a human hair. Now, the key to this device is that by carefully controlling the movement of those needles, they can penetrate the skin just far enough to draw blood from shallow capillaries while avoiding the nerves that are slightly deeper in the skin. So the idea is that the patient shouldn't feel a thing when the blood sample is being taken. Now, the needles draw a tiny drop of blood, less than a milliliter, but that's still enough for a lab-on-a-chip sensor in the device to measure blood sugar levels, and it sends that information wirelessly to a computer or even to a monitoring instrument worn on the wrist, and it can be hooked up to an alarm so that the patient or a doctor is warned if blood sugar levels start to get to dangerous levels. Now, Minchev and Kaler hope to start working on making this gadget much smaller, till perhaps it might look like a sticking plaster or a band-aid. You can just stick that on your arm, and that would sort of give it this painless way of effortlessly monitoring blood sugar all the day long. And the idea eventually, which is really exciting, is to link this e-mosquito device to another device that would administer insulin, and that's that vital hormone that diabetics lack, which regulates blood sugar levels normally. And this would essentially create an artificial pancreas, which is what most of us have, luckily, that does it for us inside us. But this would be able to monitor the amount of glucose in the blood and then automatically deliver the correct dose of insulin when it's needed to the diabetic patient. So it could offer, this e-mosquito really could offer some hope for the 246 million people around the world who suffer from diabetes and for whom needles and painful, time-consuming blood tests are really part of everyday life still.
Which is very good news indeed. Thank you, Helen. Now, you've heard the old claim, excuse me, every cloud has a silver lining. But now, scientists are saying that you've got to add lead to the mix. This is the work of researchers both in the US and in Europe. This is Dan Zizzo and also Ulrike Lohmann, and they've published a paper in the journal Nature Geosciences this week. And what they're showing is that if you take substances that are in clouds, say you take the structure or you take some cloud material, they collected their clouds from mountains in Switzerland, they also made some in the laboratory. If you feed the water droplets in those clouds into an analyzer, a mass spectrometer for example, you can show that in the water droplets there's an above average amount of lead. Where did the lead come from? Well, the answer is from petrol engines, because for the last 100 years or so, engines have had lead in the fuel. We don't use it now, but people used to add lead to fuel in order to lubricate soft valve seats. That was what the tetraethyl lead did. And the lead would then come out in the exhaust and go up into the atmosphere. And it turns out that lead is a supersonic, brilliant, king nucleating surface. And what that means is that if you look inside a cloud, you find lots of water droplets. Clouds form when warm, wet air rises and the air expands because the pressure drops. This makes it cool, and this means that the droplets then coalesce to make bigger droplets. Atoms and molecules come together to make the droplets. And at the centre of those droplets, you usually find some kind of surface that's triggered this to happen. And that can be bits of dust, it can be bacteria even, and sometimes even dandruff has been found in clouds. But often lead is there too, and so the lead seems to have the perfect chemistry to encourage these water droplets to form. What are the consequences? Well, that means that all of the vehicles we've been driving around here on Earth have probably made the planet a lot cloudier. And because they've made the planet a lot cloudier, clouds do two things. Not only do they increase rainfall, but they also, because they're shiny, reflect light back out into space. So what this has done is to lead to a reduction in the amount of heat hitting the Earth's surface. In fact, these researchers estimate that they could have reduced the amount of light getting to the Earth's surface by about 1 watt per metre squared, which on the scale of a whole planet could be quite significant. And this means that, effectively, by putting lead into fuel and making more clouds, we've offset some of the effects of global warming, which would have been there because of the CO2 that was being released alongside the lead from car engines.
It does sound quite worrying indeed that maybe we've underestimated the effect that we're having on the atmosphere. But I have to say, dandruff in the clouds is still weighing on my brain.
Intriguing thought, isn't it? But it's
is.
Absolutely true. There's a kind of bacteria too, Pseudomonas syringae, which make their entire life cycle. They live on plants. They have a certain chemistry which enables them to use ice nucleation chemistry. They make ice crystals form at a much higher temperature than they would do normally. So by doing that, they make holes in the leaves of plants, which allows nutrients to come out of the leaf of the plant that the bacteria consume. Then, when the wind blows, the bacteria go up into the clouds. They loiter in the clouds using the same ice-triggering trick to make more droplets inside the clouds, which by then have carried them hundreds of miles away. They then rain down the bacteria on a new patch of clouds, a new patch of grass, and the whole process starts again. And so these bugs have evolved to make clouds. And scientists thought that was the end of the story, but also if you take careful samples, you can detect samples of our own skin in clouds, dandruff from us and animals.
Extraordinary. Well, spitting at the dinner table might be the height of bad manners for us humans, but in the dolphin world, it's quite acceptable. That's because researchers at the Worldwide Fund for Nature, or WWF, have recently discovered that rare snubfin dolphins from down under get together in groups and spit for their dinner. Well, the snubfin is a very odd-looking dolphin. It's around 6 feet long, and it has a big melon-shaped head and, as you might imagine, short, stubby fins. And very little is known about this extremely rare species, and it's in fact the only endemic dolphin species in Australia, so it only lives in Australia. And it was actually discovered only in 2005, and up until then it was thought that the Australian populations, which people had seen, it was thought they belonged to a different species, the Irrawaddy dolphin that lives in rivers and areas in Southeast Asia. But now scientists have begun to unpick some of the secrets of this mysterious dolphin, and they've seen them hunting in groups of 6 or more. Now, working together, these dolphins seem to chase fish up towards the surface of the sea, and then they herd them towards other dolphins by spitting out jets of water from their mouths. Sometimes they apparently shoot up in great big plumes right high into the air, and sometimes straight across the top of the sea surface, but they're definitely doing it to scare the fish towards each other. And it's this kind of cooperation behaviour that's really quite rare. The Irrawaddy dolphins do a similar thing, but to see animals feeding together in groups, really cooperating between them seeing dolphins do this is quite a rare thing, and using water is even stranger. But
is there something about their anatomy that means that they can do this water jetting trick, or could any dolphin theoretically do that? It's just this particular group have learned this technique and they tend to pass it on to subsequent generations.
I don't think we actually know. I don't think anyone's actually been able to get that close to any of these guys to look more carefully at how they do it. But it's a very good question. I imagine it could be something that they might be able to do anyway. I mean, we'd have to ask someone who works in an oceanarium, in an aquarium, to see if captive dolphins perhaps play with water and perhaps they spit it out occasionally. That's possible.
Because one group of dolphins have learned to put sponges on their noses, and that's the females, because they ferret more on the seabed and are more likely to injure their noses. And I remember you telling everyone it's quite funny, because if you look at them, you see these sponges on the ends of dolphins' noses, which they pick up, put there, protect their nose, and then they don't bash themselves on the seabed.
Yes, ingenious. They are very clever creatures. They definitely have an intelligence that exceeds many other wild creatures. But the sad thing about these guys, these snubfins, is that we know so little about them, but they're already under a huge amount of pressure, and the WWF are very worried about plans to extend a port in Townsville, which is an important part of these dolphins' range, and that's on the east coast of Australia. And various other things like construction of dams and dredging of estuaries and so on means that these dolphins really face quite an uncertain future, which is really quite a shame because they seem quite extraordinary, and I'd love to see one myself in the wild spitting for its dinner.
Although, having said that, hasn't Australia declared a very big area of that Pacific seaboard to be a big marine conservation now? So actually, perhaps things won't be as bad as that
well,
in the long
hopefully,
run.
yes. The Great Barrier Reef is one of the largest marine protected areas that we have, and there is a large area that is set aside for conservation, but I think the dolphins don't all live necessarily within those protected areas, so that also is something to consider.
Thank you, Helen. Well, also this week, worrying news about what's going on in Mexico. We've seen the emergence of a form of flu, H1N1, but it's not the form of flu H1N1 that we normally see seasonally in humans. This form seems to be a swine, a pig form of the virus. So far, there have been 1,000 reported cases and maybe as many as 50 deaths. And it doesn't just seem to be confined to Mexico, because cases have also now been reported in a number of US states, including the adjacent California, also Kansas now, and also maybe even New York. So we're looking to see exactly what's going on, and joining us is from Cambridge University, internationally renowned flu researcher Paul Diggard, who's going to hopefully shed some light on this for us. Hello, Paul.
Good evening.
Welcome to The Naked Scientist. First of all, can you just explain for us, actually, what is swine flu? Because we've got our head around bird flu as a risk. How does this compare? What is it?
Well, swine flu is influenza A, same as human flu and bird flu, but it's a form that's adapted to infect pigs. So history says that pigs have had flu for at least the last 100 years or so, and when you look at the genetics of those strains, it's pretty clear that actually the viruses that infect pigs, we've been swapping them backwards and forwards between pigs and humans for quite a while.
So in the same way that birds have their strain of flu which occasionally jumps into us, pigs have their strain of flu which occasionally jumps into us, and vice versa. It's a giant sort of genetic melting pot, and in this occasion, this strain we're seeing in Mexico is a pig virus that's jumped out of the pigs and into the local population.
Probably. I mean, the virus that's been found in people in Mexico and in the US, genetically it has some characteristics of swine flu, but that's not the same as knowing that it's come directly out of pigs into people. We don't really know where it's come from yet.
So speculating for a minute, just talking about the mechanisms as to how it could have arrived, how could it have got out of a pig and into a person in terms of to arrive at the sort of genetic situation we see with this virus now?
It's speculation, because I don't know. I don't know if anybody knows what has actually happened in Mexico, but the usual route is it's people that work in the pig industry, in the pork industry. They have close contact with pigs. That's it's direct transmission from animal to man, or vice versa.
So someone who's a worker goes to work and comes into contact with a pig. The pig gives that person a pig virus directly. What about the other way around? If the person gives their human flu to the pig?
Same situation. Influenza in pigs is very similar clinically to human influenza. It's a respiratory disease. The pigs have respiratory distress. They run a temperature. The virus is probably transmitted by much the same route. Aerosol, perhaps. Just general close contact will get the virus from one organism to another.
So if a pig has got its own form of flu at the same time as a human form of flu then infects the pig, is it possible the pig could act like a sort of mixing pot and you get out of that a hybrid virus which combines the worst bits of both?
Yes, that's the theory. Pigs have been viewed as a mixing vessel for quite a while, partly because we know that we can swap viruses backwards and forwards between pigs, but even worse in a way is that pigs are also susceptible to quite a few strains of avian flu. And when you look at the genetics of the viruses that you find in pigs, it's pretty obvious that not only are they swapping genes between swine and human flu, but they're also mixing in avian genes as well, avian virus genes.
So is that why we should be more worried about a form of the virus that's come from a pig than just a normal human flu then?
What makes the current swine flu more dangerous is probably that it's antigenically novel for the human population.
Meaning it looks totally different. We've never seen anything like this.
So you and I, and probably most people will have already had H1N1 flu, but they'll have had the human strain. And at the moment it's not at all clear whether that gives you any protection from infection with this swine H1N1.
And the fact is you've got to catch flu for the first time at some point in your life, and most people don't die when they catch the flu. An appreciable number do, but most don't, luckily. So why should this one be worse then? What's giving it the edge?
Well, we don't know that it is worse. What we know so far is that there's perhaps 60 deaths or so, but we don't know how many people have been infected, so we don't know what the mortality rate is. It could be no more virulent than current human flu. It's just that there's a large number of infections that haven't been noticed because they've not been severe enough for the person to go to a doctor.
And based on what we know about the flu historically, and that history has a habit of repeating itself, we've had a number of pandemics over the years. The most famous that we've got defined is the 1918 Spanish flu. Estimated 20 to 40 million people died with that. How does this event fit with what we know about those previous pandemics?
First off, we don't know that this is going to be the next pandemic. I mean, there's a real chance it could be, but we don't know. It could just burn out. It could go nowhere. Obviously, that's what you'd hope. If it does turn pandemic, then it would be different to the 57 and 68 pandemics because those were hybrid viruses between an avian strain and a human strain. Genetically, I don't think we can say that we've ever seen a pandemic starting from a pig virus before. The 1918 virus, we don't really know for sure where it came from. Probably avian, but it's hard to say because we don't know what the virus before was.
But is there any reason why the next pandemic couldn't start with the pig?
Oh, no. I mean, I think there's a reasonable chance that in a year's time we'll look back and think, yes, this was the start of the 2009-2010 pandemic.
Let's hope not. Thank you very much, Paul. That's Paul Diggard, who's a flu virologist at Cambridge University. And this is The Naked Scientists with Chris Smith and Helen Scales.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and me, Helen Scales. There's also another way to listen to The Naked Scientists, and you can chat about the science in the show with like-minded folks at the same time, and that's in the virtual world of Second Life. We're live at 10 a.m. Second Life time every Sunday, so if you want to join us, sign up for Second Life, visit the Scilands, and then search for The Naked Scientists, and you can drop by our mansion, relax on one of our sun loungers, and listen to the show.
Yes, we're watching you lot in Second Life, so keep your questions coming in. If you'd like to get in touch with us through more normal means of communication, the email address is chris@thenakedscientist.com.
This week, we're looking at the things that you might find in the atmosphere. And later on, we'll be joined by Stephen Ashworth, who's using lasers to look at the chemicals above the ocean and find out how these contribute to environmental chemistry. But first, Ben Valsler met up with Joe Dix, who's the scientific officer for Cambridge City Council, to find out how they currently monitor the air we breathe in urban environments.
Monitoring levels of environmental pollutants is vital not just for scientists to understand what's going on in our atmosphere, but also for everybody that walks past a bus station, anybody that wants to build a new building, everybody who thinks that we need a new car park. And so I've met up with Joe Dix, who's the Principal Scientific Officer for Cambridge City Council, outside one of their monitoring stations. So Joe, what do we have here?
Well, here we have 2 units measuring PM10, which are small particles, and oxides of nitrogen, both of which are, in this location, predominantly vehicle pollutants. We're quite close to the bus station, and this is actually the site at which we measure the worst pollution in Cambridge currently.
Well, we can certainly hear lots of buses going past us, and we're next to a huge green box. How does this actually work?
Well, the particulate monitor draws air in through a filter which separates out the smaller particles. It then collects the dust on a filter which is on the end of a glass tube which vibrates at a certain frequency. As dust is deposited on that tube, the frequency changes, and that's what the device actually measures.
So the change in the frequency of this vibration will tell you what mass of particles you have that you're collecting from the air?
Absolutely, that's what it measures, mass, and it gives it in real time.
So this can measure the particulates that might be coming out of the back of buses or various other sources. What else do we measure here?
Well, we measure oxides of nitrogen, and NO2, nitrogen dioxide in particular, is the one that we have a health-based standard for. In Cambridge, we actually have an air quality management area because of high levels of NO2, which is only formed by combustion, and principally it's formed by vehicle combustion in the city. That's the main source here.
So right here we have the one measuring centre. Are there more of these across the city?
Yes, we've got 5 locations like this, one at our office, which is part of a national network, and 4 others fairly central.
So how do you actually collect the data from this? Does somebody have to come round and plug themselves in and pick it up, or does it transmit back to the council?
No, we've got a modem linked to all of these sites, and it's actually collected by a contractor who then quality assures that data and sends it back to us. We do get a daily digest of the information, but we also then get 6 monthly and annual ratified data sets.
How much does one of these cost to run?
Well, they cost about £50,000 in capital outlay to buy the whole set, and then about £3,000 or £4,000 a year to service.
And this will give you a good measure around each and every one of these sites, but obviously we'd like to know in a bit more detail about what might happen, say, to somebody walking through Cambridge Town Centre.
Absolutely. I mean, we're very interested in people's actual personal exposure to air pollutants, and a fixed site like this, whereas it gives you a good picture of what's going on at that particular location, it's very poor about showing what day-to-day exposure people actually get. You're then looking at someone's actual exposure, you're also seeing where the high points of exposure are, and that could then dictate which route they take to avoid these peak areas.
So once we have this sort of information, the information you're collecting from these base stations, as well as potentially information from somebody walking around with a handheld monitor, what can we use this for?
Well, we can use it to inform planning decisions and also perhaps cycling, walking routes, but also where we then monitor in the future. We wouldn't want to be putting a great deal of new housing into an area that's already got very poor air quality without mitigating that in some way. And likewise, we wouldn't want to be sending extra buses down a route that's already heavily polluted.
So if I was proposing building a new shopping centre somewhere around Cambridge city centre, what would I have to do to make sure that you say it's okay to build it?
Well, you would certainly be required to submit an air quality assessment, and that would involve monitoring the background levels prior to development and then modelling the impact of the development upon the air quality situation locally. At the moment, we would ask for a small diffusion tube survey to be carried out to inform us of the background levels in that particular locality.
How do the diffusion tubes work?
Well, diffusion tube is just a very simple device. It has a small grid with a bit of reagent on it, which we then hang on a lamppost. It absorbs a pollutant, in this case nitrogen dioxide, over the period of exposure, and then it gets sent off to a lab to be analysed. So it gives us maybe one data point a month or one data point a fortnight, depending on how often you change the tube.
So, say I have found the site that I want to put my shopping centre, I've put a series of these diffusion tubes around, and I've given you 3 months' worth of data showing how much nitrous oxide there is in the air. What next?
We would then ask the area to be modelled, and we use this dispersion modelling, which is a mathematical modelling, but it requires validation with monitoring information. So we run a model with the new traffic flows in place and use the diffusion tube data to validate that model. But diffusion tube data, it's very low resolution, it's not very accurate. You get sort of plus or minus 20% accuracy with it, so it's extremely ballpark, and it's not very good for validating models. The devices that we've been working on recently would enable much greater data resolution, much greater accuracy, temporal resolution, and it would allow us to pinpoint the areas where the pollution would be worst.
And so with this higher resolution data, you can far more accurately predict the impact that my new shopping centre would have.
Absolutely, and we're talking about very, very small changes which can make a great deal of difference.
So what do you see as the future of environmental monitoring?
Well, obviously these fixed sites with very accurate reference methods are always going to be important. We've got 11 years' worth of continuous data from these sites in Cambridge, which is a great wealth of information. But a combination of much more mobile monitoring and a greater spatial array across the city will undoubtedly inform our decisions better in the future.
That was Joe Dix, Principal Scientific Officer for Cambridgeshire City Council, explaining that although static environmental sensors give us constant, high-quality data of how clean our air is, they're rather expensive, and they can only tell us about the air immediately around where they're placed.
Indeed, thank you, Helen. Now, Professor Rod Jones, who's at Cambridge University, has been working with Cambridge Council to find a way to fill in these gaps. And he's been developing cheap mobile environmental monitors to really show how much pollution each person could be exposed to.
Well, the big issue that we're really looking at is that we know that air quality can impact on human health on the one hand, and actually on the radiative properties of the atmosphere. And the bigger picture still, I guess, is that we know that as we look into a future climate, we're likely to see changes in air quality. And so what we're looking at is trying to understand some of the basic principles associated with what controls air quality, and ultimately, I guess, how we might take steps to try and mitigate changes in the future.
Air quality can be considered in two ways, though. There's the air quality on the scale of the whole planet, and then there's air quality just around town. So are you looking at everything, or are you just looking at one small component there?
Well, some of our work actually looks at the global issues, but this particular project is much more focused on local air quality. So it's the kind of air that we breathe in cities and in urban environments. And
when a person takes a walk down the road in the average city, what sorts of things are they being exposed to?
Well, a range of gases, things like nitrogen oxides, ozone, of course, particulates, and those are the main gases which I think are causing people concerns.
So how are you going to study them?
Well, of course, the problem is being studied at some level, but a lot of the equipment that's needed to study it is big, expensive, and complex to run. And so you can only locate measurements of that kind in a rather sparse network. And so what we're trying to do is to look on a much smaller scale, on the order of meters, and more than that, we're trying to introduce sensors which we can carry around in our pockets to monitor how air quality is changing and how the air we breathe is changing actually as we walk the streets.
Because that's going to be a much more realistic measure, isn't it? Because if you just sample one area, if the traffic isn't in that area or the wind's blowing the other way, you're going to miss a load of stuff. People don't stay in one place, they move around, so do cars.
That's right, and there's a certain amount of evidence that even which side of the street you're on will determine to some extent the exposure to pollutants that you're going to have.
So what's the strategy? What have you got to do this with?
Well, what we've adapted really are sensors which are actually used for monitoring of dangerous gases. And they're very small sensors in themselves, so they're very amenable to being put into very small packages. And so we've basically got a handheld device which weighs perhaps 200 grams, which actually has on board GPS, which we're all used to using in our cars for location, and in fact the guts of a mobile phone, which is termed GPRS, which allows us to transmit the data from these little boxes to a central computer in real time. So in fact what we can do is to give people who are involved with the project these sensors to carry in their pockets and wander the streets, and we can actually map the pollution that they're being exposed to, and in fact others around them are being exposed to, in real time.
And how do you then put all that data together? How does the system actually work to compile real-time data and link it to geography?
Well, of course, the GPS tells you where you are. And we can now map the pollutants that we see, or the pollutant levels that we see, onto even simple things like Google Earth. And so that you can see precisely where the high levels and low levels of pollutants are. Of course, it's never that simple because, as you said a moment ago, standing in one point, the pollution varies quite widely, but we're able, at least at some level, to pick up that as well.
Are you actually getting data yet, or are you just at the stage where you have got prototypes of the devices, now it's ready to go out in teams of people to see what the pollution looks like?
The stage that we're at is that we actually have pretty advanced prototype sensors, which include, as I said, the GPS, GPRS, so the communications and location. And we have them in sufficient numbers that we can actually pretty much inundate a city. Where we're not quite there yet is in the sophisticated analysis software that you need both to analyse the data from a scientific perspective and to produce something which somebody can log onto the web and actually see in a web page what the pollution for a particular time of day or what they might be expected to be exposed to if they lived in a particular part of a city is. And we're working very rapidly on that. So we're hoping to put together the whole package, but it's not quite the finished article yet.
How are you going to use it? Is this going to be giving pedestrians these devices? Is it going to be giving cars these devices? Because obviously they're going to see different levels of pollution. And what sort of resolution are you able to get? Because can you literally see someone walking on a pavement versus someone in a car on the road?
Some of the sensors are certainly capable of detecting those the differences between being in the centre of the road and being on the pavement. But I think really what we're aiming for here is to produce a network of sensors, some of which will be static, in fact, But any kind of platform, moving platform, as well as lampposts, for example, would be used to provide us with a very wide range of data for this very complicated environment. And you could envisage somebody walking down the street with their mobile phone actually using Wi-Fi or the internet to pick up a map which gives you real-time pollution.
And that was going to be where I was going to go next, which is to ask you, well, how is this going to guide either replanning of towns and cities and traffic flow or how humans behave?
Well, there are a range of activities which could be influenced by this. If you have a sophisticated network of air quality measurements, then you can actually use that to begin to understand how that links into the detailed traffic flow, and ultimately you can think about controlling traffic flow to minimise the hotspots, the pollution hotspots. At another level, you could actually use it to begin to map out, if you like, the lowest pollution path between your place of work and your house. And so somebody in the morning can get up and look at the web and decide which is the preferred cycling route, which is going to give them the least level of exposure to pollution. That's a dream for the future, but it's not that far in the future.
And do you think you'll see yourself one day in a position where you will be able to go up to the developer who's about to put in a new housing estate and you will say, don't build your roads like that because we know that will create a greater pollution problem than if you plan like this?
Well, I think we, in a sense, have a responsibility to try and answer those kinds of questions. How clear-cut an answer you can get for some of the questions that you've just asked, I'm not really sure yet, but we ought to be able to derive a general picture of how to, for example, build a housing estate in a green fashion.
Indeed, and also get to work with the least inhaled aerosol pollutants, which sounds good news to me. That was Professor Rod Jones. He's at Cambridge University's Chemistry Department. He was explaining to me there how his handheld devices could make sure that new developments are built in locations that will do the least environmental damage and also let people plan their healthiest commutes or even the cleanest walk to the shops.
Later on, we'll be hearing from Mira Sinthalingham, who joined Rod for a walk around Cambridge, armed with one of these monitors, to see how they collect data and how it can be used. And still to come, Stephen Ashworth will be joining us to explain how marine organisms contribute to our atmosphere and how a neat trick with lasers can help study miles of coastline without even leaving the lab.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and me, Helen Scales. And we've heard a lot about the portable sensors that Rod Jones and his team are using to monitor pollutant levels whilst walking around a city. So let's now join Mira Sinthalingham to see how these sensors actually work in action.
Yes, so I'm now here at the Chemistry Department at the University of Cambridge with Rod Jones, and we've got one of these handheld devices in front of us. And there's a lot packed into here. So what have we got here? At the top, we've got the 3 sensors. What are these sensors detecting?
Well, the 3 that you can see here are detecting nitrogen dioxide, nitric oxide and carbon monoxide. Inside each sensor, there's a small amount of fluid, which is called the electrolyte. And when the gases enter the sensors, they actually force a very small current to flow in that electrolyte, and you measure the current. So you can relate the current from this, which is very small, to the amount of gas that you're trying to detect. And of course, this box does rather more than that then, because what it has to do is to take that current and digitize it so that we can then transfer it to a computer. These boxes actually also determine where we are using GPS that everybody knows. And in fact, there's a Bluetooth connection here, which then links it to a mobile phone, which is sitting just next to it now. And it's that mobile phone which transmits the data from the sensor in real time to a central computer so that we can look at it.
Now, you've managed to pack all of this into not only a light box, but its size is actually quite small. It's only about 15 centimetres by about 5 centimetres. And you're going to take me on a particular route around Cambridge so we can see these devices in action. Where are we going to go?
Well, we're going to go from the chemistry department, which then enters immediately a busy road. We're going to walk towards a major traffic junction and then into an area which is green park area, really. And these are typical of the kinds of places that we've been making these kinds of measurements.
We're outside the chemistry department now with the handheld monitor. Rod, how are you going to turn it on? What should we do before we start our walk?
Well, I've just turned the phone on and it now shows me a screen which I can then use to detect the sensor box. And the sensor box I'm just switching on now by pushing one single button. And in a minute, there we are. It's telling us that the device is working and has actually detected the GPS satellites So we're now ready to go.
OK, so let's go. We're heading down towards a particularly busy junction. Now, I can imagine that the sensor will be particularly active right now.
Well, yes, the chemistry of the atmosphere is really quite complex. A lot of these vehicles are going to be releasing a fair amount of nitric oxide, and so we might expect to see really quite high values of nitric oxide. And of course, individual cars have very different emission amounts. And the age of a vehicle really matters as well. And if a vehicle is old and not particularly well maintained, it's quite likely that the emissions from that are going to be much higher.
It is very busy here. There are numerous cars, motorbikes, lorries, trucks just going by. But now we're going to head over into the quieter Parker's Piece.
It's very interesting because if we're trying to understand how the chemistry of the troposphere works, we actually have to look at a lot of different sources, and immediately you can see that we have trees and greenery here, all of which can emit a range of different molecules which can affect the chemistry of the troposphere. So we need to get the complete picture, and this little box is part of that process.
We're now in the middle of Parker's Piece, which is a very large green area here in Cambridge. Now, it's much quieter, the cars are much further away, but, they're still not that far, so surely the pollutants are still going to be reasonably high here.
That's right, and in fact we can feel a slight breeze. That's obviously going to bring the pollution from the road, which we can see just over there, into Parker's Piece. We're not likely to see quite as big fluctuations in the emissions from vehicles because they've now tended to mix out a little bit.
As pleasant and sunny as it is here, we now are going to go back to the lab in order to look at the information of this particular route. We're now back in Rod Jones's lab in the chemistry department, but joining me now is Mark Kalea, who's a software developer on the project. So Mark, you've got your laptop with you here, and it's got Google Earth on it. So on your Google Earth now, we've got a satellite view of the area that I just walked with Rod. What are you going to show me on this particular view of Cambridge?
Right, here we're going to have a time-dependent plot of someone walking around with a sensor, and we're going to just show the nitrogen dioxide track, just to show the difference between walking, say, in a quiet street or next to a traffic-laden street. We've colour-coded the data points, so it goes from dark blue, low pollution, to pale blue, to white for medium levels of pollution, going up to pink, and dark red means high levels of pollution.
So this particular video we're going to watch is just showing one person wandering around Cambridge. The person is shown on the map as a circle, and this circle is moving around as the person is moving around Cambridge. Now, to start with, this circle is dark blue, which means that the pollutant levels are actually quite low.
It so happened at that time, yes, it was. It's mainly dark blue for the route this person's chosen, except when he gets to quite a busy street, which is just off Parker's Piece, and then it starts going to pinks and reds. And it's not unusual. Wherever you get high levels of traffic, that's when you expect your pollution levels to go high. As you can see, as you go down to the by streets, the pollution levels drop.
But as you say, this is for a very specific moment of time. So how can you collate this information into something a bit more usable?
What we'll do is we can plot all data points from a time window on one graph and then post that graph on the relevant map from Google Earth. And that will allow us to have a fuller picture of what happens over, say, a day or a week.
And Rod, actually, you've got one of these graphs for the particular route that we've walked today. It's basically a series of lines around the city, and it looks like a wall or something has been built around it, and variations in the height of this wall are basically the variations in certain pollutants.
Well, that's right. As Mark was saying, what we've done here is just to plot on top of a Google map a vertical line which represents the amount of pollution at a particular point. And so as an individual walks around the streets, you can see a line which follows them walking, and the height of the line above the surface represents the amount of pollutant, in this case carbon monoxide. And here in Gonville Place, that was the place that we stood with all the traffic flowing around. In fact, we see the highest amount of carbon monoxide, around 2 parts per million, which is way, way above the natural background. But you can now see where these sensors really come into their own. So if we now look at a map of nitric oxide, what we see, in fact, is really very high concentrations of NO, close to where the bus station is. But now when you follow our walk into the centre of Parker's Piece, surprisingly, the nitric oxide values drop really quite low. What it means is that we're further away from the vehicles which are the primary nitric oxide sources. But now if we look at NO2, which is one of a gas of considerable concern in terms of health, we suddenly see that the NO2 values in the middle of Parker's piece are in fact every bit as high as in the surrounding areas. And in a sense we expect that because what we're seeing is the reaction of nitric oxide with ozone to give us NO2, and so the NO2 values kind of hold up as you move away from the direct pollution sources. But everything actually depends critically on the subtleties, the wind speeds, the meteorology, the specific vehicle that passes you by.
What are you going to do with this information in the future? Could it be the case where someone could just log on and plan their route according to the levels of pollutants they see?
Well, that's one of the ambitions, I think, of this project, so that anybody, anywhere, can actually determine by looking at the web what their likely pollution exposure is going to be.
So if this technology develops further, you could have a clear picture of where pollutants are highest and therefore where to avoid, not only in your own city, but many cities around the world. That was Professor Rod Jones and Dr. Mark Kalea showing me at St Thillingham just how these portable sensors work and how we can use the data with Google Earth to get a detailed map of local pollution.
Laying the facts bare. I say. The Naked Scientists.
So, we've heard about the developments in monitoring pollution in enclosed urban environments, but other systems also contribute to the quality of air across the country. And Dr. Stephen Ashworth is from the University of East Anglia in Norfolk, where he studies the gases that come from marine systems to find out how they contribute to the chemistry in the air around us, and that means on the scale of the whole planet. Stephen, hello, welcome to the Naked Scientists.
Hello.
So, what are the big questions you're trying to answer?
Well, this work came out of a campaign that goes ahead at Mace Head. We heard in the piece just a moment ago about the natural background levels, and one thing that's very important for us atmospheric scientists to know is what those natural background levels are. Now, one place this is done is at Mace Head in Ireland, and the idea behind that is the prevailing wind is from the Atlantic, so there's very little pollution. So on days when it's blowing from the west, we can get a very good idea of what natural background levels of various components of the atmosphere are. But one thing that came out of one of these campaigns was there were very high levels of particles detected, these aerosols that we've been talking about. And having detected these particles, the question was, what goes to make them up? And it turns out that these particles have a lot of iodine in them, and the iodine was traced to the seaweed on the foreshore at Mace Head. The question is then, is this a local phenomenon, or does it affect the whole globe?
So what you're saying is that iodine, which is coming presumably from the sea, could be getting into the atmosphere and clouds, and therefore triggering things like cloud formation, and therefore influencing rainfall.
Exactly. Certainly these seaweeds give off a lot of iodine in compounds, and that iodine then gets processed by the atmosphere and turns up in these aerosol particles, and they're just the sort of surfaces you were talking about right at the beginning that would enable water to condense and form clouds. How
does the iodine get out of the seaweed and into the atmosphere?
Well, it seems that this is a mechanism against stress. If the seaweed feels stress, it releases these compounds, and one of the things that stresses seaweed is the tide going out. So they tend to get dry and release compounds containing iodine.
So that would then be blown up on the prevailing wind into the atmosphere, where it would then have downstream, excuse the watery pun, effects on the weather.
Yes, exactly. The sun shines on these compounds. The light is the interaction with the light of the sun that causes the iodine to be broken off these compounds. It then turns out that it reacts with ozone in the atmosphere to produce iodine oxides, and they're what go on to make up the particles.
So how are you trying to understand more about this iodine and to understand more about the chemistry as to how it gets into the atmosphere and how much of it there is?
Well, the idea here is that we can measure in the atmosphere what's there. We want to answer the question, how was it produced and what's it going on to make at a later date with interaction with other chemicals in the air, with sunlight and what have you. So we need to take things back to the laboratory and make these compounds under as controlled conditions as possible and analyse how fast they react, what they react with, and what they turn into once they've reacted.
And how are you doing that?
Well, we can mimic this process by producing ozone in a sample cell and feeding in some iodine-containing compounds. We can also mimic sunlight in the laboratory fairly well, and we find that we make lots of particles. Another experiment that we've done is to actually try and break down the production of the particles into a series of steps, and so that we build up the iodine oxides one step at a time. We find to do this, these compounds don't absorb very much light. This is how we measure how much we've got and how fast it's reacting. We use a laser to see how much light is absorbed.
Oh, right, so you know that different chemicals absorb laser light at different wavelengths. So if you shine a laser beam of the right wavelength through it, the amount of laser light that gets soaked up must be proportional to how much of the chemical is there.
That's exactly right. Because we need a lot of chemical in this case to actually see the change in the laser light, we have to do a little trick by trapping the laser light between two mirrors, and that makes it bounce up and down through our sample lots of times. And if we're lucky with the right combination of circumstances, we can get effective length, so it makes it look as though the sample may be 10 kilometres long.
Has anyone actually done this in terms of really shining a laser beam through 10 kilometres of atmosphere rather than bouncing it on a light path 10 kilometres long between two mirrors like this?
There are experiments which do that. You can shine a laser beam 90 kilometres up into the atmosphere and get a signal back in an experiment called LIDAR, but it's a slightly different principle that's involved there.
But do the results agree? So you think you've got a good model with your mirror bouncing system to accurately predict this important aspect of atmospheric chemistry?
Okay, I misled you a bit there. The LIDAR results aren't actually used on the iodine chemistry, but we believe through modelling, again, we've heard earlier in the programme about various modelling that can be done. By modelling the systems using the results from the kinetics that we measure, how fast these reactions go and what's produced, we can be confident that we have a fairly good understanding of this system.
Ingenious. Thank you very much, Stephen.
My pleasure.
That was Dr. Stephen Ashworth, who is from UEA, University of East Anglia, working on ways to detect the chemicals that are important to climate and the Earth's atmosphere as a whole. Helen.
Still to come, we have Diana with our question of the week, when we'll be finding out if magnetic devices can stop our pipes from furring up.
Bringing the facts to bear. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Helen Scales. We've been talking this week about the science of the atmosphere. In just a second, Diana will be here to tell us whether attaching one of those magnetic devices to your water pipes can actually stop them furring up. You'll notice also that we have dispensed with kitchen science this week because we sent Mira out with one of those atmospheric measuring devices to see how they actually work. But on the subject of kitchen science, we did have an email from Randy Heisch, and he wrote to us from Georgetown in Texas, and he said, I tried the kitchen science this week. He's talking about last week's show, and I have to say it was just about the coolest experiment ever. So thank you to Dave and everyone for bringing us this, and still enjoying your show. You do a great job. Please keep up the good work. Randy actually took photos of the straw fountain pump that we created and told you how to make, that Helen tested on the programme and actually didn't know what was going to happen and got a bit damp.
Totally soaked. Thank you very much, Dave. Yes.
And Randy has taken some pictures. He used a drill to power his pump, and so the pumping ability was absolutely phenomenal, but he's taken some of the most beautiful pictures, and Ben has put them on the website, nakedscientist.com/kitchen science, if you want to take a look at Randy's straw pump actually in action with the beautiful pictures.
Homemade garden sprinkler, I think. Fantastic. Well, it's now time to invite Diana O'Carroll back into the studio for our question of the week. Hello, Diana.
Hello, how's it going?
Good. Lovely to have you.
Great. Well, this week it's all about magnets on pipes. So how can you shave your plumbing?
My name's Tony Rogers, and I live in Dereham in Norfolk. I've been told a magnetic field can dissolve limescale in water pipes. Is this true, and how does it work? Since the pipes and I believe the limescale are ferrous and not affected by a magnet or a magnetic field.
So can magnets really clean out your pipes?
I'm Hugh Hunt from Cambridge University Engineering Department. Well, there are lots of manufacturers' websites that claim that if you put magnets on your water pipes, then that prevents limescale build-up on the element of your immersion heater. Well, it's obviously in manufacturers' interests to make these claims, but let's suppose that in the last year a manufacturer has sold 1,000 of these devices, and they get one letter which says how fantastic it is, another 10 letters that say that it doesn't work. Well, they can give 10 refunds. They've still made quite a lot of money, and they can publish that one nice letter, and I guess that might be what we're seeing on the websites. But now that's being a bit mean, but I'm a bit puzzled that there aren't any quoted, refereed scientific publications out of the mainstream literature. Surely if there was something really scientific going on here, it would be well and truly understood. So I just wonder. Now, there are a few possible candidate theories, all to do with magnetohydrodynamics and water memory and things to do with nucleation and so on. We can read all about these. Where does that leave us? Well, I think if you have found that one of these devices works for you, well, it doesn't do any harm, so you may as well carry on using it. But if you find that it doesn't work, then perhaps there's no surprise in that.
So nothing's been published to show that these do or do not work. And here at The Naked Scientist, we couldn't find much in the way of reasonable explanations for how they might work.
I really like the way that Hugh was really concise and actually straight down the line said it's like this in his answer. Decisive answer.
Yeah. What you didn't see there was he actually had like a little glass bulb with some mercury floating around in it, and that was another interesting way to deal with limescale. But unfortunately, as with this, no real explanation for why it might work. But on the forum, Wolf Keeper said that even if there was an effect on the water, it would be moving too quickly through the field for any anti-furring to occur. But that's it for magnetic fields. So what about the gravitational field?
Hello, Naked Scientists. My name is Christophe Boutillier from Utrecht in the Netherlands. My question is, do we and objects weigh less at night time? I could imagine that the additional gravitational upward pull of the sun during daytime will work to a certain degree against the downward pull of the Earth.
Do we weigh less at night? I'm sure many of us have experienced it on leaving the pub, but can we literally drift to sleep? Answers on an e-card to chris@thenakedscientist.com or on the forum of answers at thenakedscientist.com/forum.
What a brilliant question. Thank you very much, Diana O'Carroll, with this week's Naked Scientist Question of the Week. And if you like Diana's Question of the Week, you can find it on the web as its own podcast. Question of the Week on iTunes. About 5,000 people a week are availing themselves of your Questions of the Week, Diana, so please go and join them if you enjoy it. Thank you. Now, Helen, I've got a question, it's an email for you, actually. It's from Ken, who was listening last week when you were talking about octopuses, octopodes, octopi. We were trying to decide what the plural of octopus was, because you were talking about them being all unilaterally venomous. And Ken has said there are 3 acceptable English plural forms for octopus. They are octopuses, octopi and octopodes. But my Greek wife, like Dr. Smith's Greek scholar, suggests that octopodes is closest to the Greek plural form. My mother-in-law, on the other hand, makes the best octopus. If you're in West Hertford, you can look her up. Her name is Kathy. How kind of him.
Oh, thanks very much, Ken. I think I'm going to go for octopodes too. It's fantastic. We've also heard from Paul on the text system, and he says, Dr. Chris, why is the government hell-bent on electric cars? He says, to me, the science doesn't make sense. It's not greener, as the production of electricity can be dirty from power stations, and the short life of batteries, they're very expensive to replace and difficult to dispose of. What do you think of that, Chris?
Well, I think that Paul has a point, which is that there's no such thing as a free lunch. If you're using energy, it's got to come from somewhere. But the benefit an electric car offers is that it doesn't produce pollution once it's working as an electric car. Obviously, the pollution is all in one place, the power station, and that means that mitigating strategies to recover the waste from the power station, the CO2, the particles, etc., can be done locally, where the power station is, and probably more effectively than fitting scrubbers and things, which will be less efficient to a car. And also, individual cars are all going to be inherently less efficient than one giant power station. So it's a sum of lots of little inefficiencies adding up to a bigger inefficiency than one big inefficiency, the power station. So that's why we think electric cars are beneficial. They also are much better in traffic because stopping and starting burns enormous amounts of fuel, wastes enormous amounts of energy. Electric motors are absolutely perfect for that kind of thing because they don't waste energy when they're not actually moving. Now, I've got a question for you, Helen. This is on the environmental theme. Jack Stowe says, will global warming cause water levels in rivers to rise too?
Well, what's going on in the rivers and streams and lakes and sort of fresh water inland is a different process than in the seas, because what they rely on mostly for the levels of them is the rain. It's all about whether it's going to rain more or less. And one of the things we really know about climate change and what's going to change in the future is that there's going to be a difference in how different areas respond. Some will become drier, there will be less rain, and some will become wetter, there will be more. And we're already seeing this. In some areas like Australia, we're seeing huge amounts of droughts, rivers are drying up, and that's likely to become even more prevalent in some areas. But there will be also rain increasing in some parts of the world. So it will definitely vary and not be a sort of general increase in sea level that we will see. The sea levels are rising, of course, because actually as that huge mass of water heats up, it will expand and sea levels will go up, and also more water will pour into the oceans from the melting ice caps and things like that. So really the picture in the rivers will be very regionally diverse, and it will depend on where you are in the world.
So bottom line is rivers are down to rain, sea level is going to rise anyway because of thermal expansion and ice melting.
Yes, that's right, yeah.
Thank you, Helen. Well, I'm afraid we've run out of time. That's it for this week's Atmospheric Naked Scientist. Just remains for me to say thank you very much to our contributors this week, Paul Diggard from Cambridge University, Rod Jones, also at Cambridge University, and Mark Kalea, and also Stephen Ashworth, who is at UEA. And thank you also to our wonderful production team, Ben Valsler, Tom Simpkins, Mira Senthillingham, and Diana O'Carroll. Next week, we turn to the science of engineering. We'll be finding out how scientists make very powerful turbine blades made of just a single crystal, in some cases, of the metal nickel, and that gives them enormous strength and means that they can spin round at unfeasibly high speeds to make jet engines pack the punch that they do. Howard Stone from Materials Science at Cambridge University will be here to tell us how that works. And we'll also be talking to a guy who's managed to make what people thought was impossible actually possible. That's to make an articulated lorry, a double articulated lorry, actually turn corners. You might think that's a simple feat, but it isn't. In fact, if you try and make a lorry which is double articulated go around a corner, in fact, the second trailer ends up pointing the wrong way. But with this new system that the engineering department have come up with, they can do it. Find out how it works on next week's Naked Scientist.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.